Welcome back. In this session, I'm going to talk to you about automatic variable selection methods for regression. When faced with a large number of independent variables to choose from, it can be a daunting task to pick out which are important, which are not important. And just dumping in all the independent variables into regression using the default enter method can lead to some erroneous conclusions. So we'll find some methods here to automatically pick out relevant variables for regression. Before that, a little bit more about the intuition behind this method. A good regression model must be one that includes relevant variables. A variable that is expected to have an influence on the dependent variable. At the same time, a regression should not include non-relevant variables, variables not expected to have an influence on the outcome variable. The second bullet point is probably obvious. The third bullet point is about regression should not include redundant variables. Non-relevant, redundant, is that just tomatoes? Not really. A redundant variable is one that has been rendered redundant, maybe because it was non-relevant to begin with, or because of the presence of extreme multicollinearity. There are situations where a variable that was otherwise predictive loses its power because of the presence of another variable. This is exactly what happens when you have multicollinearity. Let me use a soccer example. In a game of soccer, one of the most important positions is that of the person covering the goal, the goalie or goalkeeper. Now, a team might feel like, well, maybe they should have two goalkeepers in the team. Clearly, for anybody who's watched soccer before, you understand having two goalkeepers wouldn't make any sense. But work with me on this little analogy here. If the game of soccer were like a regression model, if it saw two goalkeepers, it would look at them and evaluate them and realize the two goalkeepers performing the same role in the game of soccer. As a result, their effects would kind of cancel out. Using some statistical terminology, they would have high correlation between them. The model as such would then have high multicollinearity with respect to those two goalkeeper variables. Whenever you end up with a regression model with two variables that have a high correlation between them, you have high multicollinearity. This leads to erroneous conclusions, strange results. Your results might indicate that neither goalkeeper is useful in predicting the outcome of the game. That wouldn't make any sense. We know that two is probably not better than one, but having two doesn't just negate the value of the goalkeeper altogether. That wouldn't make any sense. But that's exactly what happens when you have high multicollinearity. So what we're looking for is variables that are relevant, basically have statistically significant regression coefficients, and that are not redundant, ones with VIF values that are manageable. To get some sense of what I'm talking about here, let's take a look at what happens if you were to take our data of hotel satisfaction and run a regression with it. You'll recall in the previous session, we had a video of where I ran a regression of all the aspects of the experience against overall satisfaction. Let's do that one more time here. So here, and let's analyze regression, linear. I'll remove the stuff I had before in this window and move in all the satisfaction variables tied to aspects of experience and move the dependent variable to dependent. Click on statistics, check VIF, get the VIF values from collinearity diagnostics, and hit OK. Here we have our regression output. Now, the regression R squared is 0.329, which is significant. Moving along, in the coefficients table, you'll notice now we have some variables that are significant, some that are not. The ones that are significant are relevant. However, relevancy cannot be judged purely based on this picture, because some variables that may have otherwise been relevant may have been rendered redundant because of high VI values. It doesn't seem to be the case here, except for this one that's threatening. None of the VI values are above 5. So as such, the VI values are not too high. Right? That being said, anytime your VIFs are not perfect, a perfect VIF is 1. By perfect, I mean a model with 0 multicollinearity. Granted, having 0 multicollinearity is unusual almost. It's ideal, which is probably what makes it unusual. It is practical to have some levels of multicollinearity. It is when the numbers get to be too high that we worry that these results of the p-values for individual variables may be attenuated, or maybe rendered to be too small, making them non-significant. To address this issue, we have a couple of methods possible. So one thing we can do is use theory. Maybe there's some sort of theoretical background that tells you what variable is useful, not useful. You only put the relevant variables in. If you find two variables that are equally or relevant, but they're and also redundant, you choose one or the other of them using some guiding theory. An alternative is to use a variable selection method. There are a couple of them. One of them is the forward variable selection method. The way this works is we add variables to the model one at a time. And as we add variables, we look for the marginal improvement in the model. If we feel the marginal improvement is not significant, we stop adding more variables. In this picture here, I've got a little cartoon type model going on. We have here 8 independent variables labeled x1 through x8 and 1 dependent variable y. What you can do here is examine in this example, fictitious example, how the process plays out in regression. So the first thing that happens with the forward model is, as soon as you put all the variables in, you bring the variables to run a forward regression model, it will evaluate every single variable individually and look at its relationship to y. In this case, we have color-coded represent how strong each variable is related to y. So x1 and y have a strong connection, hence more green. x3 and y have a very weak linkage, so red. Now, when encountered with this sort of relevancy measures or associations, regression using forward method would make a choice. It would bring in the most predictive variable into the model first. x1 will go in first. Now that we have x1 in the model, we have an r squared of, let's say, 0.3 coming out of this. The question would be, which variable goes in next? The choice of which variable goes in next will depend on what variable makes the largest marginal contribution to r squared. In other words, we're looking for, after accounting for the effect of x1, what other variable will give the biggest bump in r squared. So based on that notion, what we can do is look at now re-rating all the 7 remaining variables. Accordingly, you'll notice out here x6 has been re-rated to be a red. x6 may have previously been significant or been somewhat relevant, but now with x1 accounted for in the model, it is no longer a useful variable. x4 has grown in importance. So the next variable to go in the model would be x4. With x4 in the model, the r squared goes to 0.4. The question now is we reweight all the other remaining independent variables and evaluate how influential are they in affecting y after accounting for the effects of x1 and x4. Based on that, we conclude that x2 is less relevant than before. x8 is about the same. Okay? We got to make a choice now. Which of these two, x2 or x8, they both seem pretty close together, is going to give a significant boost in r squared. The model goes on now and adds on one more variable, x8, which brings the r squared to 0.45. The model will go on now to the next step and again reevaluate the remaining 5 variables to see if they were brought into the model, what will be the bump in r squared. The red colors indicate bringing in any of these remaining 5 variables would not lead to a significant or marginal improvement in r squared. Therefore, our model stops here. The forward variable selection method here has chosen 3 variables to enter the regression model, x1, x4, and x8. Let's actually use an example to evaluate how this method works. We're now going to go to our data. Here we have our variables we ran before. We're going to go to Analyze, Regression, Linear. And here's what we had before for the enter method. That is the default method in regression. Let's change that to forward. And let's ask for some more statistics. Check the box for r squared change. That's it. So in here, we have all the satisfaction variables related to aspects of experience, and we have overall satisfaction. Our method is forward. We're asking for some statistics here. Okay. Here is our output window then. You can see out here the process involved. Now, as you saw, we added variables one by one to our model. The same things being represented in this table. The first variable to go into the model is front desk staff, then elite perks, then clean room, then dining price, and so on. Bottom line, we're adding variables on one at a time until we get to a point of diminishing returns. 10 variables were entered in the model, and then it stopped. Let's see the process. In this model summary table, we have a summary showing us the process of adding variables into the model. First variable to go in was front desk staff, and that took the r squared from 0 to 0.256. I'm saying 0 because in the absence of any variables, r squared would be 0. Remember, that's your baseline model. And therefore, the r squared change, 0.256 minus 0, is 0.256. That difference or improvement is statistically significant. Our next row talks about model 2. Model 2 contains 2 variables, front desk staff and elite perks. In other words, the second variable to enter our model is elite perks. This improved the r squared to 0.277. Now, 0.277 minus 0.256 is 0.021. That difference is statistically significant as well. In other words, the marginal improvement in the model was statistically significant. Going along, we're going to add on the next variable, clean room, which makes r squared go to 0.294, an improvement of 0.018, which is significant. Next, we add in dining price. R squared goes to 0.306, improvement of 0.012, which is also significant. On to city, R squared goes to 0.312, which is a significant improvement of 0.007. Adding in hotel points next leads to an improvement of 0.004, which is also significant. Next, we add in housekeeping staff, and that also results in a significant improvement of 0.003. Next is clean bath, and after that is Wi-Fi price, and lastly is distance from transportation. We can see as you add more variables on one by one, the R squares go up, and every time the R square goes up significantly, that variable is added on to the model. This is how we end up with 10 variables in a model. Ultimately, our R square leads to 0.326, and the last addition results in R square going up by 0.002, an improvement with a p-value of 0.043. Now, when you end up with this increase of 0.043, that is deemed as being significant. At this point, the model decided not to add any more variables because adding in any more variables would probably have had an R square increase that is non-significant. So automatic variable selection is automatically chosen for us the variables to go in the model. Let's take a look at the coefficients table, actually a ANOVA table. The ANOVA table is going to show us the overall R squared from every one of these 10 models. Remember, the 10 models indicate a growing number of independent variables in our model, going from 1 through 10. The coefficients table shows the progression. We can see here, first model only had front desk staff, second model had front desk staff and lead perks, and so on and so forth. And lastly, our output here has model 10. Model 10 is our final model, so I'm going to highlight that model here. So this is what the forward method regression has told us. It's told us that the variables that are significant are these 10. These 10 are predictive of overall satisfaction. Now, you'll also notice one more thing here. We have more variables here in the model than we had from using the enter method, which is telling me from the enter method, some variables may have been incorrectly dropped, or they may have not been able to get to statistical significance because of multicollinearity, albeit modest levels. Okay, so that's the forward method for variable selection. Our last model is always our best model, the one that we're going to go with. Okay, let's go on to a second variable selection method. This one is called the backward selection method. The backward selection method works in backward kind of process, in the sense that instead of adding variables one by one to the model, we add all variables to the model and then cut them one by one. A nice analogy to understand this process is to think about the those TV shows where like America's Got Talent and American Idol and so on, where they cut contestants one by one until they're left with the last contestant. Contestants are dropped based on lack of performance. But we begin with everybody on stage at the very start. The difference is that in backward selection method, we don't have to end up with just one contestant. We could be left with 10 variables or 5 variables. The point here is backward method will stop cutting variables whenever it feels like cutting a variable will make the model significantly worse. Let's understand this then. Analyze, regression, linear. The only change I'm going to make to this window is make the forward method to be backward. Click OK, and let's switch over to the output window. Here we see in the output window In the very first step, all variables are being entered. And then in model 2, 3, and so on, we're going to cut variables one by one. The first variable to get cut is valley staff, then room price, then so on. Let's examine the R-squares through this process. So in our very first model, you see a very busy footnote. It's busy because our very first model has a lot of variables. In fact, our first model has all the variables in it. With all the variables in the model, the R-square is 0.329. Now, as opposed to forward model, in the backward model, we're hoping our model doesn't get worse when you drop a variable. So in the first round of cutting, we drop one variable. When we drop that one variable that is noted in the table above, the R-square drops to 0.329 from 0.329. In other words, there's almost like not a noticeable effect drop in R-squared. It might be in the 4th or 5th decimal place. Either way, whatever that drop is not statistically significant. In other words, dropping that variable, I think it was valley staff, from model 1 did not lead to a significant worsening in the model. So we drop it. In fact, we keep giving the model a haircut step by step unless the model gets significantly worse. So you see in model 3, we drop another variable and the model remains pretty much unchanged. In step 4, same thing, no change. We go on along doing this, you see that as we go to do this thing, at some stage you'll see some of these numbers become to be, a little larger. So you see kind of here in model 6 stage, 0.327, and the drop is 0.001. We're seeing a 0.001 drop in R-squared, but that is not significant, so we're not going to worry about that. And it goes on cutting variables until it gets to a point where cutting a variable does matter. So on and on it goes, cutting variables until the point where if you cut any more variables at the stage, the R-square would get significantly worse. So the final model, again, is our best model that contains these following variables. Let's take a look at that model. It's our last model here. Our last model in here is our model 8. And model 8 is going to have these variables. Let's do a quick count here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We wound up with 10 variables yet again. So I don't know if the results were any different for forward method. You can do a comparison here of the variables in forward method versus the backward method. It turns out, at least in terms of the number of variables, we have the exact same number of variables left in the final model as the forward method. On to a third method. This third method is called the Namestate stepwise method. This stepwise method runs forward and backward methods simultaneously. So imagine you're adding variables one by one. At any stage, you can also cut a variable. That's forward and backward, both in sync in a stepwise method. Let's take a look at what happens when we run this. We go regression, linear, select the same menu of method and change it to stepwise. And off we go to our output now. Our output shows us that we have gone through here in this results, adding in variables one by one: front desk staff, lead perks, clean room, dining price, city, hotel points, housekeeping staff, clean bath, Wi-Fi price, distance transportation. Now, it's really odd that this column here of variables removed has no variables noted. That basically means that the model kept adding on variables one by one, but didn't find a reason to drop any variable. Hence, you have no variables removed. And you see your model summary looks very much like the forward model summary. In fact, it's probably identical because we haven't dropped any variables along the way. So you can see out here, you would add variables one by one, hoping to see addition resulting in a significant increase. And if you were to reduce or cut a variable, it should not make the model much worse. Our final model is the last model, model 10 here, which like we saw, which we saw before, we have, I believe, the same exact model we've gotten from all three methods. That's not unusual. It's commonplace. It's fairly common that the three methods usually converge on the same selection of variables. Okay. So to wrap up then, we've examined here these three variable selection methods. They, generally speaking, will leave you with the exact same results for whether you use forward, backward, or stepwise. You'll typically get the same results coming out of the exercise. All right. So thank you for joining me. Happy regressing.